Hi friends, let's have a look at problem 34. Find first and last position of element in sorted array. So this is a daily challenge problem. So actually, personally, I like this problem very much. So in this video, we're going to share a method based on binary search. So here we're going to emphasize the logic of search range shrinkage. So I marked the method as binary search plus tailored search range shrinkage. So this problem asks us to return the starting and end position for a given target value. So if the target is not found in the array, so we're going to return -1 and -1. So here he said that we must write an algorithm with logarithm runtime complexity. So in example 1, so the 8 appears and the left index is 3 and the right index is 4. So in example 2, so target 6 does not exist in the nums array, so the return is -1 and -1. Example 3 is a special case, so corresponds to an empty array, so the return is -1, -1. So the constraints on this problem are mainly about the length and the nature of the nums array. So the length is bounded above, but it can be reached to 10 to the power 5, a decent large number, and nums is non-decreasing. So that's the main statement as a constraint. So now let's look at the method. So actually, in general, or for general binary search, so here the very typical paradigm. So there are two ingredients in the binary search. So the first is how to produce order. So this is typically defined by defining a Boolean monotonic function. So this monotonicity of the function actually produces the order. So here we're talking the first item. Actually, it's in a much wider context than the vanilla binary search. For example, if we search if a target is inside the array or not, the array is sorted. So this is item 1. So item 2 is the search range shrinkage. So this is actually also very essential. So for both of the two items, I would suggest that you watch the videos in my playlist, and hopefully those videos can expose you the general logic. So here in this video, I'm going to put an emphasis on the search range shrinkage. So because this problem in some sense is simple. If you could grasp the thoughts in this video, so you shall be able to solve quite a lot of problems related to binary search. So our plan here is to solving the problem from scratch to digest the search range shrinkage logic in general. So I'm going to write two functions. The first function is to fetch the leftmost index if target exists in a sorted array. And the second function is to fetch the rightmost index if the target exists in an array. So in between, there will be line-by-line instructions. So I hope that you can watch closely to grasp the logic. So with that said, let's first do the thing first. So first is a function so that fetches the leftmost index if target in array, right? So for this, I'm going to define it as f, just to see we have nums, which is a sorted array, so some elements can be repeated. So let's use a goal. So this is an element we want to search. So let's assume the goal is in nums array. So here what we want to do in this function is to find the minimum L such that the nums L is greater or equal than goal, right? So if the goal exists in this number, if we choose very large L, for example, the end index of nums, so this is true. So we want to try to shrink this L so that we can find the minimal such L, such that nums L is greater than or equal to this goal. So notice that the directions of the equalities are important. So with that said, let's initialize the left end and the right end as routine. So nums -1. And then we're going to do the while loop. So while L is less than R. Then what we are going to do is that because we know if we choose the right end, so this condition will be satisfied if goal is inside the nums array. So what we are going to do, we are going to increment from the left. So we are going to try L, R minus L, so integer division by 2. So the condition we're going to check is nums made. If this is greater than goal, right, then our search range for this condition, because we want to make sure nums L is greater or equal than the goal, right? So if nums made is greater or equal than the goal, then actually our search range update should be like this. So the made, so the L should be made. So this reset, we want to find the minimal one. So the R will be the made. The reason is that the search range update. The search range update here is if this condition holds, notice that this is greater or equal, right? The same direction as this one. Then if this condition holds, we're going to search in L to made. Because made is still possible, and maybe the one, right? We should include this made. So we set R equals made, and we search from L to made, because made satisfies this condition, right? So otherwise, so if this condition is validated, means that nums at made is less than the goal. Then because we assume that nums is sorted in a non-decreasing fashion, we should set L to be made +1. So the search range update to made +1 to R. Why we +1? Because made does not satisfy this condition, right? So that's it. So notice that in this pattern, so the left end or the variable L is always satisfying this condition, right? It's possible that finally at our return, nums L is strictly larger than goal. In that case, it corresponding to the situation that the goal is not in the nums array. So we should always return this L. So this L is the minimal L such that nums L is greater or equal to this goal. So this is the first function. So we're going to write. So this let's first postpone a little bit to do the check. So next I'm going to write another function so that fetches rightmost index if target in array. So this function is slightly different, but I hope that we can compare the differences of these two functions. Here I'm going to call this function G, nums and go, right? So again, I'm going to assume that this nums is sorted in a non-decreasing way, and the goal is inside the nums. So if it's not inside, so we're going to treat that later. So in this situation, so what's the logic? The logic is that we want to find the maximum L such that so nums L is less or equal than the goal, right? So we want to find the maximum L such that the nums L is less or equal than the goal. For example, in this one, we want to find the maximum L such that nums L is less or equal than 8, right? So this is the one corresponding to index 4. So in this case, again, let me initialize L and R. So then what we are going to do is that we do the while loop, like if R is greater than L, then we're going to move from right to left. So I'm going to do R minus L over 2. Then the check is the following. If nums made, so the same direction as our goal here, because we want to find the maximum L such that nums L is less or equal than goal. So if this is the case, then what we want to do, we want to set L equals made. So let me make a remark. So it's a search range update. So because we want to find the maximum L such that nums L is less or equal than goal. So currently at the midpoint, this condition is still satisfied. Then we're going to move to the right, but we still need to include this L or the middle. The reason is that the middle can be the final target, right? So the range will be made up to R. So that's the update. Otherwise, then it means that this condition is violated. In other words, nums at midpoint is greater than the goal, strictly. So we're going to set R equals made minus 1. The reason we set R equals middle minus 1 is that we want to update the search range to be L made minus 1. Why don't we include this midpoint? The reason is that at midpoint this condition is violated, right? So notice that in this structure, the R or at variable R, so this condition is always satisfied. So we're going to return R, right? So that's the second function. So notice that in these two functions, our goals are different. In the first function f, our goal is to find minimum L such that the nums L is greater or equal than the goal. And you notice this check condition here and the return here. And in the second function, our goal is to find the maximum index L such that the nums L is less or equal than the goal. Notice the direction of the inequality. And then notice the consistency here. So we are also checking against this condition, right? So here we are checking against this greater or equal condition. So this condition will aid our search range update. So let me emphasize again, right? So in the first function, the goal is we want to search the minimum L such that this condition holds. So the principle is that as long as this condition holds, we're going to put the range to the left. So in the second function, we're trying to search maximum L such that nums L is less or equal than the goal. So if this condition holds, we're going to put the range to the right as long as possible. So that's the principle. So let me rephrase this principle. So in this case, so if we check nums made is greater or equal than the goal, then so this condition is still hold, then we want to put to the left, but we need to include this midpoint. So we set R equals made. And if this condition is violated, then we're going to search in the right side. So we are going to update L to made plus 1, right? So in the second function, because our goal is to find the maximum possible L such that nums L is less or equal than goal. So if this condition holds, then we're going to push to the right, and then we need to still include this midpoint, right? And then if this condition is violated, so we can only search from the left. So we're going to set r equals mid minus 1. And notice that the interpretation of L and R. So in the first function, the L is always making this condition true. So we return L. And in the second function, the R is always making this condition true. So we are going to return R. So with that said, I guess I explained quite a lot about these two functions. Now let's look at the return. So if not nums, so this nums is an empty array, right? It's possible because the length can be 0, or if we find the left index, for example, just to use one of them. So let's first do left array equals f nums target and g nums target. So if the target exists in the nums, then we're going to have the at left or right, it must equals to the target. So we just need one check. Nums left does not equals to target. So this if condition actually summarizes the cases that target does not exist in nums. We're going to return -1, -1. All the other cases we're going to return left and right. So that's it for this function. So let's do a special case check. Yeah, it passes this one. Now let's do a generic case check quickly. So it passes all the cases. So one hint is that, so if you are still confusing, so you can try to print out this left and right to check all the different cases. So here let's maybe emphasize again. So these two functions actually both perform at logarithm time, and they serve different purposes. The first one is search fetches the leftmost index if target in array. The second fetches the rightmost index if target in array. So the key point is to first keep the goal clear in your mind, and then update the search range accordingly, and then interpret L and R with relating with the goal. So you will be clear which end we should return. So in the first one we return L, in the second one we return R. You notice that the search direction is also slightly different. So in the first function we search by increment half and half, and in the second one, so we shrink by half and half. So basically that's about it. So I hope that this video can be useful for you, and it clarifies something. So you are encouraged to look at my playlist on binary search. So hopefully those examples there can shed more light on this topic. Thank you so much.